and talk about computability and transformers and circuit complexity revival. Floor is yours.
Thank you. Michael and I have known each other for 15 years. You wouldn't believe that, but that's one of my oldest colleagues. And we only started collaborating together on science stuff, not drinking stuff last year. So that's good progress. We're aging, it seems. The goal of this presentation is to tie transformers, like the famous T in GPT, with concepts of computability that you may be more familiar with, in particular Turing machines, circuits, temporal logics, all of these things that will make sure I reintroduce when needed, even if it may not be. So the final goal is to reach some of the results we have with Andy and David from Notre Dame. These results talk about the expressiveness of transformers in a very classical way. In particular, a work that we just submitted this month is studying what kind of regular languages we can express with transformers. This is that classic in a way, right? So we're trying to reconnect transformers, all these voodoo models of computations, with something that we understand a bit more. Who's familiar with the actual definition of transformers? Yes. The first, oh no, just pretend then. So the first time I gave this presentation was in front of pure mathematicians. None of them, and in the same way, had any understanding of what is the definition of the model. We understand that it works beautifully with our everyday use, but what is the mathematics that is behind it? It's actually quite a few layers of weird maths, and I will try to abstract this from a computational perspective, in a sense that the operations that each layer is going to do is pretty simple, just like linear transformations. Okay, so I will lie a little bit. This is my preface here. I will lie a little bit. So the goal of this presentation again, oh no, oh, there you go. Okay, is to succinctly present transformers as recognizers, as deciders of languages in the very classical sense we used to, and tie them with two very traditional notions of computability: Turing completeness. So one of the first results about transformers just stated, I think was the title of the article, transformers are Turing complete. But there was a caveat to that. And the caveat is when allowed to think. And you may be familiar with that if you've interacted with ChatGPT. It's like thinking for and thinking and thinking and thinking. There's been a movement recently of some researchers are like, do not use that term anymore. It is it's making them more humans than they are. So thinking is just a way for a transformer to re-eat what it just produced. Let's see that in a second. So if they're allowed to think for an unbounded number of steps, they're Turing complete. If not, then if they have to produce an answer immediately, they're actually very weak in terms of computational power. I'm going to see that in a minute. So transformers, they live in the very tiny computational world of low complexity circuit classes. And this is a huge difference between the two, right? Turing complete, and this is within log space. Okay, so there's that caveat there of just when allowed to think is not just a detail. It is very important to the computational power of transformers. Our interest is mostly in that because we can say a lot of things if we don't allow them to think. Okay, so in that case, we'll be able to actually tie transformers explicitly to some temporal logic, which is a formalism to express some languages, some problems. I'll go over a few examples. And at the end, we'll derive a depth hierarchy for transformers. The deeper a transformer is, the more expressive it is. So we'll have to have a notion of depth for a transformer. You may be familiar with that picture. We have the inputs at the bottom for transformers for some reason, and there's multiple layers of so-called attention. And what we're seeing here is the more attention you have, the more layers of attention you have for transformers, the more powerful they are in the very classic sense. That's the plan. Any questions? Yeah?
What do you mean by
think in terms of the thinking about the circuit.
Yeah, what is thinking is a good question. How do you formalize that concept for a model of computation? I will be answering that. Well, any other question I should answer? Except the yeah.
Yeah, campaigning, I mean, you put them at the top of the food chain, when they have an allotted time to perform their magic. And then when you don't leave them any time to think, they get to be very weak. Is there anything in between?
So that's an interesting question. Can you bound the thought? Because this is really, if you allow them to think for unbounded number of steps. If you bound a number of steps, we have some results. It's not as much explored as the unbounded or the completely bounded case. But you can have regimes that are in between. And they're realistic from the application point of view. When you ask a question to ChatGPT, usually you wait 10 minutes and you're like, well, I better get an answer, right? Nowadays on ChatGPT, by the way, you have this thinking mode. You can activate, I want extended thinking time. And then the transformer will eat itself, its output so many times. But there's also a small button that appears on the side that says answer now. And this is for you to just stop the computation. And this is really reminiscent of the halting problem. It's just giving you the hand. It's just like, oh, you don't have to tell me when to stop. And so the theory of having like a polynomial number of thinking steps is studied. This is not studied in that work. It's studied. The results are not super clear yet. The results I'm presenting are, so they're not officially published because NeurIPS has a weird way of publishing stuff, but they've been presented at NeurIPS last year in December. And I can say that for something that was presenting in December, this is so old. This is so outdated. So things go very, very fast in that small community. The community itself identifies as FLAN, Formal Language and Neural Network. And there's a community, a Discord server, and talks around the formal language and neural networks community. All right. So let's get started. I'll introduce quickly what is a transformer. Again, I want to be frightening, but not too frightening. I want to be frightening enough that you don't ask questions about why, but understandable enough that you understand what is in that. Then we'll go and have a look at the infinite, unbounded, rather, thinking time. Then the no thinking time at all. And I'll conclude with some open questions. So transformers. I'll simplify a lot of things, but from the outside point of view, this is just a function from words, sigma stars, the set of all sequences over the alphabet of symbol sigma, and I obtain a real number at the end. All right, this is one of the first things that a transformer would do. You may be thinking, oh, but they usually compute some multidimensional thing. Well, sure, but the multidimensional vectors are within the execution of the transformer, and at the end we just pick one of these as the answer of the transformer. So they have multiple layers, each of them accessing the previous layers, and these are called the attention layer. So that's the term from the original paper. Attention is all you need, and the attention layer is a combination of 2 or 3 linear transformations stacked onto each other, then a feed-forward neural network, which is basically a max function. Okay, so the graphic you're going to see in all the papers, all the first papers on transformers, looks something like this. Full disclosure, I didn't write the ticks for that. ChatGPT did. And that's only fair, right? So you have an input token sequence at the bottom, and that's your query. For instance, you're asking how many S's are there in my sequence? And you just write the sequence. The first step that is being done by a transformer before getting to the alpha function here is to transform that sequence of symbols. So we have, no, not so fast. We have a mapping from symbols to d-dimensional vectors. And so this symbol, for instance, if it's tokenized, you may be thinking that that map is mapping the word house to a vector that's for which one dimension is about objects. And so it has a value in that dimension because a house is an object, not a concept, for instance. And maybe there are like 200 dimensions for 200 classification of words. So this is done on the token side. And this is simply, in our case, extended for each of the input symbols. So at the layer 0, we have multiple layers here. At the layer 0 over here, we are just encoding position I. So this is the ith wire with the d-dimensional vector that corresponds to the ith input. Okay, so E is just seen as a mapping from token to vectors. And here we have a sequence of vectors. And this is our first very basic layer. Cool. All right. What's next? What's next is a self-attention layer. And these are the most complex layers in this whole thing. The self-attention layer will compute information based on tokens that appear. Oh, they didn't art. That appear before that. So that token, that's a vector here, will be a combination of all the vectors that are in previous positions at the input. The way this is done is in a multi-step process. There are two. Okay, let's look at this. There are two matrices. These matrices have dimension. Yeah, there we go. D by D head. Head is for hidden. That's the hidden dimension. And I'm converting my first vector here to another vector of dimension D hidden by applying simply a linear transformation. Just a matrix times the vector I had before. And that's my key at position I. All right. Again, I don't want you to argue with the definition because it is what it is. It just works. Not my problem. We just look at it. What I want you to focus on is what are the computational primitives are needed in order to compute these. And this is just computing a linear transformation. So this is fairly easy to do, right? Evaluating a such a transformer is pretty much what we're interested in. So this is the key at position I. This is Q for the query at position I. We'll now take some sort of product of the key and the query together. And we do that using a function with two parameters this time, a layer with two parameters here. This is the current token, and this is the token I'm attending to. So what is the relation between the token in position I and another token that is somewhere else? And this is called the attention of position I to position J. And that's the query times the key. And that's just a real number. Okay, so that's what they mean by attention. We're saying, oh, this token at that position attends to or has an attention over the token at position J. And that attention is just a real value that is computed in such a way. All right, there's more. Now that I have how much I is interested in J, we over here, we're still trying in the self-attention to produce a new set of vectors here. Now that I know how much I is interested in J, I will just weigh that by what is called, and it's only that's the last parameter pretty much, by the value. This is again taking the previous layer, applying a matrix here. And this gives me the value at position I. All right. Then you combine all of that. Finally, the layer above. So realize that all these matrices here, so the query, the key, and the value, I have one per self-attention layer. That self-attention layer is equipped with one big matrix Q, one big matrix K, one big matrix P. And then from that, I have pretty much the next layer. The next layer at position I, okay, it's unreadable I now, This is how it is. I didn't want to lie too much, right? This is the exponential of the attention of position I, that's the one I'm interested in, attending to position J. And critically, importantly here, J is any position is before I. So any position I will look at the key query product times the value of what happens before. And this is simply then weighted by all the, so this is with the value, this is without the value. All right, so this is just a way of scaling it. Okay, simple operation. Again, it's just a repeated sum. And then I have some exponentiation. Okay, we're thinking computationally. We are talking about real numbers. So already we're thinking, oh, maybe this is fixed precision, or the precision is a rational number, you have a numerator or denominator. How do I implement this? But this is pretty much it. The last thing, concluding the self-attention layer here, is a feed-forward neural network. So this is just paired with a feed-forward neural network and this is of very simple complexity. This is just, think of it as a max function. It's just making sure that whatever value I got is bounded by some constant value. That's what the feed-forward neural network is. This, my friends, is a self-attention layer. We get as inputs a layer of vectors from R to the D. We combine, for position I, we combine all the previous values. This is that combination here. We combine, we fix my query for position I, and we take the product with the key at position J for J smaller than I. This gives us what is the amount of attention that a given position I, gives to other position J. We weigh that by some value. We make some sort of average sum. And we make a threshold with 0. Think of it this way. That's it. This is a transform. All I need to do now is repeat this thing with multiple other layers. We repeat. And the output function, you can take something as stupid as what I mentioned before. Oh, I will take it. That this column over here is not just for using space. I'll just put a reminder here. We'll not be looking a lot at the attention layer, but just as a reminder, for each position I, I'm computing the score against another position J. I weigh that by a value. This is my V here. And I take some sort of average, which is called, that function is called softmax. With the feed-forward neural network. So, other layers, and at the end, one output function, and my output function is just taking one dimension and outputting. And that's it. Yeah?
You're presenting this as the causal way, like attending only to the J's that happened before. Any reason for that? Because we can also attend to all of the J's, like even the future.
So I'll come back to this in the conclusion, actually. But this is a very important restriction. We're saying a position only relates to the positions that appeared before. And this makes some sense in there you go. So this is what is called future masked. You cannot see the future of my computation. This makes sense when we want to produce more tokens and more tokens and more tokens, and every time treat them as thought. All right, so we do not know what will be produced. So this is the reason this is looked at. It is called decoder only.
So you're presenting this as a language model, not necessarily an end transformer.
Correct.
Only language model.
Correct. And we'll see that this has a huge impact actually on the ability of the whole community of being able to say anything about these models. If we didn't have that, the equivalent model to this will just simply be normal circuits, and we do not have lower bounds, meaningful lower bounds against circuits. So this is a critical point. Yeah. You had a question, sir?
Yeah, well, I mean, I'm wondering about the semantics of the inputs. So is this a sequence that is temporal in nature? I mean, is this, prompt after prompt after prompt, or is it something that is available to the transformer all at once?
So the all at once, the feature here is just,
Yeah, so
Restricted by that.
question, I guess.
Yes.
Right? Okay.
but this is the only restriction we have. Position at the beginning does not know what is happening next, right? And yeah, this is what in the literature is called decoder only. The encoder is something that has access to a whole thing, encodes my input, and the decoder would be decoding step by step. Yeah, most of the things that are implemented nowadays in practice are decoder only. So the takeaway here for me, okay, we may have something more on that, is that a transformer is some input encoding, some attention layers, some bipolar neural network, and we alternate these things and we output it. So conceptually, it is a machine that just takes an input sequence, produces vectors in the middle, according to some fixed schema, and at the end outputs a real value. Are we good with that? Right? So I'm lying only on very small things here. One thing I'm lying about is that this here is usually not just the encoding of the token. It's the encoding of the token and some way of encoding the position of the token. The simplification I'm making here is not super important for the theory, but in practice it would. So I'm gonna talk a little bit more about that towards the end. So that's the main simplification I'm making here. The second thing I'm not talking about, I just mentioned it in passing, is that these are not what computers can actually manipulate. We don't have real numbers. We don't. We have fixed precision numbers. We have rational numbers if you want to. So the way this is encoded as real numbers may be important for theoretical results. If we have any real number, then of course I can have as my embedding function something that encodes an undecidable real number, like an encoding of the sequence of all halting Turing machines, something like that, right? So we have to have some sort of restriction on this. And the usual restriction is to say, oh, we're doing fixed precision or variable precision, but something that is like manageable by a computer. All right, transformers, beautiful. So what happens with transformers when we want to use them? We train them. What it means is that these, the depth of that transformer, that is the number of these layers, is fixed. I'm saying 42. And so I have 42 matrices Q, 42 matrices K, 42 matrices V, and I have some parameters in the fitball neural network. All of them are initialized with, let's say, random values. And then I'm training my blank transformer, 42 depth transformer, by tweaking these parameters over a huge amount of data for which I have the input and the expected output. All right, the training is not really what I want to talk about here, only because I don't know nothing about it. Yeah.
And when you say 42 layers, you mean I need to apply for Q2 on Q1 and the layer 0? And
so that's exactly that. So we obtain the layer 1 here, and then repeat everything with layer 1 here, and I have a Q2 and a query 2, a key 2, a value 2, and so on and so forth.
And Q2 apply to still layer 0?
To layer 1.
To layer 1.
Right.
Layer 1. Okay.
This is also slightly lying because the original model would have communication between layers, but they can be simulated at some costs, by only having a look at the previous layer.
And here the input token sequence, I can think about some settings you send to the.
Yes. So it's well, if you want to be closer to reality, you can be thinking of a sequence of tokens. So house is not 5 letters or so. It is just 1 token. Okay. All right. So that would be closer to the kind of classification of tokens that is actually done.
Let's see.
Yeah.
And here, then, if you're saying the house is 1 token, then you say the WI is 1 letter.
WI would be house.
Well, would be house.
Yeah.
But this one.
Yeah, my alphabet there would be the whole dictionary. So every item in Sigma is a word. Does that make sense?
But how is one other?
What house is one letter? Yeah. For a few editions it is. Yeah.
One last question, I hope.
Oh, no. Wait. I mean, again, I'm not an expert in this. I'm an automaton theorist, a circuit complexity theorist. This is not my thing. I'm presenting it so that we can spread some knowledge in this.
It's never funny, I mean, exactly the same thought, you know?
Yeah.
I'm trying to understand the concept more than the equations.
Yeah, no, exactly.
What is the meaning of those real numbers? I mean,
The meaning of?
the meaning of those real numbers, are they just arbitrary encodings that are being manipulated in some sort of learnable way, I mean, based on the matrices and that's it?
So
So the meaning is it in the eye of the transformer or is it in the eye of the user of the result?
excellent question. So the answer is we do not know what's the meaning, the semantics of these numbers. We have some experiments that give us that when a transformer is trained on specific data, then that dimension is bigger for, let's say, female nouns in a gendered language, and so you can try to extract some semantics from the actual numbers and the use of dimensions, but this is not driven by the user. It is just, it could be anything. This is at the core of the beauty of the transformer model. It's just, it manages to, during learning, specialize one dimension for one concept, for one linguistic concept. And so this is true at the lower levels. And once you have like depth 8 or something, we have no clear understanding of what the dimensions say.
The story about division.
Yeah, no. Anything else? All right, so let's start with, wrong direction? Oh, no. Okay, so now that we have transformers, I want to just mention what is thinking. And what is thinking, or what is called chain of thought, right, is just conceptually for us, letting T generate a token. So the first output here would be one more token. And we let it generate one more token until it outputs a token accept or reject. So we interpret that value here as a token. So this should be a classification. Or if it's between 0 and 1, then it's a token A. If it's between 1 and 2, it's token B, and so forth. And if it's between 42 and 43, this is the token accept. So we look something like this. I have my first input, and it computes, and outputs 01, some token. Then I feed it again with the whole input, and now I have 01 passed as an extra input. And I have an O2 that's being generated. And I do it again, and again, and again, until at the end here, we have something that is accept or reject. Right? This is the chain of thought model. And it has different names. I think the literature has now stabilized after 3 years on chain of thoughts, despite some fights on over certain thoughts. And so that's one possible model of computation that uses transformers as its building block. All right, this is the same transformer. This is still the same transformer at every time. It's T, that's T, that's T. Notice that the model I presented, I didn't bound the input size. The only thing that was bound is the dimensions D and the hidden dimension D hidden, right? But the rest, I could have had any number of tokens as input. Doesn't change anything. Okay, so this is one possible way of seeing a language theoretic side of transformers. Or you can just say, let me just get one transformer and say, I want to have all the words for which the output here is greater than 0. It's a real number, can be positive, can be negative. All right, I want all the words that are mapped to something that is positive. So these are our two different types of recognizers. Chain of thought, or just tell me whether you accept the word or don't accept the word. Right? So I want to build, for instance, a transformer for all, it should output something positive if the input has ABA. It's a sequence of A's and B's, and it should accept, so return something positive if it has ABA in the word. All right. These are our two models. And we're asking where, so I have my model of transformer, it's fixed. This is what it is. If I'm looking at that way of accepting languages, what is the complexity of that? What is the complexity of these languages? And if I'm accepting just with that, what is the complexity of these languages? And we have answers for these two things. The first one, so what can transformers compute if we give them time to think? And this is unbounded many steps. We just wait for them to end up saying yes or no. And this is an old result from 2019. That was one of the very first results of the time. So it's considered like very naive now. And the title of the paper was simply Transformers Are Turing Complete, I believe, or something similar to that. And the proof is fairly easy. Okay. It is fairly easy. I've presented the actual proof to computer scientists before. And usually computer scientists are like, after 5 minutes, they say, I see the idea. That's okay. I don't need to see the details. No one wants to see the details. No one wants to be encoding stuff with 3 matrices per layer and so on and so forth. So I'll just give the idea. The idea here is that we start with a Turing machine and we want to transform it with chain of thought that can simulate it. Right? This is the goal of that theory. So based on the first character of the inputs, just the first character, my transformer can output, so the last thing is produced, can output the first transition of that. This is actually very deterministic. So I'm just saying that my output will only attend to the first character, and the first character will tell me what is the transition that the Turing machine, which is deterministic, will be taking. First step. So this is the bootstrap. And you have to wire your matrices in such a way that this makes sense. For the working steps, at each generation step, so at each new thought that you want to generate, there's a count on what was produced before, the transitions that were produced before by your transformer. And so you will count the number of transitions that were moving the head to the left, the number of transitions that were moving the head to the right, and you subtract them. This is just setting a value of -1 for going to the left, +1 going to the right. We make the sum, and that gives us at which location we are in the head of the Turing machine. So this is how you localize the head, just using that repeated addition. And then you need to extract what is the actual symbol on the tape for that. And for that, I need to either attend to the original input or to the last location at which that position was seen. And this, there you go. This is doable by having the right keys in the right values. Right, and that's pretty much it. So every step, you rebuild the current location of the head, and you rebuild what is its current contents just by reading the previously generated transitions and stopping at the last time that cell was seen. That's the main idea. I don't want to go into too much detail. The main crux of the proof really is that I take a Turing machine and I can build a transformer that will output each transition one by one until we reach a transition to the accept state. And then instead of generating a transition, I'll just generate accept. So this, it can take an hour to get into all the details and it's not super interesting. But this is crucially requiring chain of thought. Specifically, the number of thoughts you need is the time Turing machine needs to execute. Right? So there's nothing that is but there. It's just a model that is that is able to track over a large input what was the state of a train machine. Now, let's think of a model that we know about, that more than transformers. Let's think about push-down automaton. So an automaton with a stack. We can pretty much do something similar, right, with a push-down automaton. Let's say I have my input. Okay, the first step, my push-down automaton will just check the first symbol, and so it can output. Let's say we have push-down automaton that can output at the end one symbol, can output what is the first transition of the Turing machine. And your push-down automaton can also pretty much do the second step. It can read what was the sequence of transitions that was taken and know in which location of the stack of the tape the Turing machine is. All right, just +1 with going left, -1 with going right. So on my stack, I can know at which location of the stack I am, of the tape I am. So if I had just a bit more power, I could also track what is the symbol on that tape. What I want to really stress here is that you do not need a very powerful model in order to do that kind of approach. An automaton plus a stack plus 10 more bit of memory should be able to do the exact same thing. Chain of thought as a concept, I'm outputting something that I'm reading the whole input, is very powerful. As a language variable construct, it is very powerful. Yeah.
I'm gonna say, I mean, it's nothing very spectacular, you know. So basically, you can encode that in a transition system, which is a finite automaton with countable states. You know, I mean, it's really the same idea. Right?
Yeah. There's nothing really transformer specific to this. This is what I want to stress. Yeah. Transformers may be scary, but this is not where it is scary.
It's a trick.
It's a trick.
It's not part of the transformer. It's part. I mean, the chain of thought is the one that is important.
Yes, but nowadays transformers are trained with chain of thought in mind.
Sure.
So so in that sense, you know, it's a trick. How good are they at learning any language is a different question.
That's right.
But in theory, they could implement with unbounded chain of thought. They could implement any language. All right. Any questions on that? Yeah.
That's like this, I don't want to go into the details, but I don't have the intuition of how you can count the transformer, because the numbers can get arbitrarily large.
Right. So in the attention layer, there was a step where I was summing all the for a given position. Yeah. All right. And this is an unbounded sum. All right. This is what it is. All right. Cool. All right. Let's skip to things that I actually understand myself. So what can I do if we don't allow that chain of thought? If we don't allow that trick? If we just say, okay, I'm just interested in what can you compute in one run, and you accept the word if you output a positive number, you reject if you output a negative number. And this is where the title of the presentation is coming in. This is where we can tie it into circuit complexity, which is a much more classical model of computation. This is a Boolean circuit. The inputs are usually at the top, contrary to transformers for some reason. So graphically, the inputs are here, and my output is there. My gate, so this is a directed acyclic graph. My gates are OR gates, AND gates, negations, and for purposes here, majority gates. So if my input here is, I don't know. I said, I don't know. I said, there we go. 1, 1, 1, 0. That gate will output 1 because it has 3 inputs and the majority of them are 1. It's also called a threshold gate. And this is tied to classical neural networks where threshold was the main gate in that. So the negation of, so this will output 1. This will output 1. This is 1, 1, or 1 should be 1. Here we have the negation of 0, that should be 1, and so on and so forth. We evaluate from top to bottom. The interesting thing here is that this recognizes a set of sequences for 0 and 1s, but all of length 4. So in terms of recognizing a language or solving a problem, it's not very interesting, because at most I'll get 2 to the 4 words in my set of accepted sequences. Not super interesting. So for circuits, we actually have to consider families of circuits. So one for size 3, one for size 4, one for size 5, and so on and so forth. Who gives us the circuit for size 42? I do not care. I will just assume that it comes from hell. And so this is a subset of 3-letter words, 5-letter words, and so on and so forth. And so in the end, we have a full language over all possible input sizes. These are my circuits. Now that I have a family of circuits, I can talk about how they grow with the input length. So, for instance, I can talk about the number of gates. In our case, we'll always have a polynomial number of gates, so it doesn't explode. Another measure I'll be interested in this talk is the depth. When we actually evaluated that circuit, we went like the top, then the second layer, the third layer, the fourth layer. The depth is pretty much the parallel time it takes me to do the evaluation. If I could evaluate a whole layer in one go, in parallel, then I would still need that many steps to do my full evaluation. This is the length from an input to the output, and maximal at that. All right, and these are our threshold circuits. And our depth will be set to any constants in that case, giving us the classic class of TC0. Yeah, come on, there we go. Our threshold circuits are AND gates, OR gates, negation, majority gates, polynomial size, and constant depth. Any questions on that? All right, and they recognize sets of binary sequences. What is the link? Okay. First, the very old result of Merrill and Sabawal was that any transformer language, in the sense of threshold, right, and my output needs to be bigger than 0, can be implemented as a threshold circuit family. And this is not surprising if you've been doing any kind of circuit complexity in your life and you've seen the class TC0 before. TC0, which is this class here, is known for being the class in which you can do arithmetic, right? The lower classes, not powerful enough for arithmetic. TC0, you can do your multiplication, you could do your additions, your iterated additions of multiple stuff. And so the idea of the proof is exactly that. First, we need to have some sense of what are the real numbers. For them, it's bounded precision, but not bounded to a constant. There's a your computers are usually bounding precision to 64 bits for floating point numbers. There's some theoretical results that say that if you were to bound the precision, you would have only a finite number of floating point numbers you can express, and so the only languages you could express are finitely many of them. So in their paper, they have a bounded precision, which is log of the size of the input, something like that. But this is sufficient to do all of the arithmetic operations in threshold circuits, in TC0. So all the operations they use in executing our transformers, that is the sums, the division, the softmax, the fit for all neural network, the mappings, all of that I can implement with these very, very weak circuits. That's it. That's the proof. That's so we have addition, multiplication, division, max, exponentiation. We need some encoding for that. Iterated addition. All of that is doable in that very small class. And this is again on floating point numbers where the precision is log of the depth, log of the input length, and that's it. So what they showed is that the circuit depth, the depth of my circuit, is correlated with the depth of my transformer. So if I'm interested in, and I am personally, in how does the expressivity grow with the depth of the transformers, then all I need to study is the circuit depth, right? And this is something we can manipulate way more easily than these weird matrices and so on and so forth. Just a note here, that class here is included in log space, which is included in polytime, right? So this is very, very, very low. Very low. All right, so this was ingredient 1, connection with circuits. So at the time it was like, oh, so we can import all the results from the 60s, 70s, and 80s on circuits, and this was done. It was super, super sexy. But this is not an exact characterization. There are threshold circuits that seem not to be implemented by transformers. And so in order to have an exact characterization, we have to turn to a slightly different framework, quite different framework. And this is that of temporal logic. I'll mention that with a few examples, and then I'll skip a few things, and we can finally get coffee. Coffee is, where is coffee? I got tired all of a sudden. Okay, so temporal logics are a way of specifying a language with one formula, with a logical formula. The syntax of our formula is important here. This is a word over 80, and we said that W is a model of A if the last letter of W is A. Okay, if you've done temporal logic before, you maybe wonder why it's not the first. This is because transformers have a past view of all the inputs. Let me just say it. So W is a model of A means that at the last position of W, I added A. Cool? All right. Another example. This is a counting predicate. It's counting the number of positions at which I have an A on the left of the current position. My current position is the last character. So I'm counting the number of A I have on the left of the last character. And it has to be equal with the number of B on counting on the last character to the left. So this is specifying that the number of A's and B's is the same in W. Okay. What is this? This is the number of true. So the number of positions to my left that are true. So this is just counting the number of positions to my left. And saying there's only one position to my left. Okay? And I'm an A. So this is evaluated in particular on the current position. So this is just the word A. Cool? Yeah.
By the current position, you mean the last position. You mean the last position of the string.
Everything is evaluated on the last position of the string. Right? Except that when I'm in a nested such thing, then this gets evaluated at all positions. So I'm counting the number of places where it is true that there's no character on my left and I'm A. And that has to be a 1. What is the language of this? Now he wakes up. The number of places where I'm the first position and I'm an A is 1.
First letter.
The first letter is an A, right? It's at most one position that can satisfy that, because there's at most one position that satisfies I'm the first, and I want it to be an A. Okay, so this is the first letter is an A. No more prefixes, more B's than A's can be written like this. If you're familiar with this, this is very close to well-nested parentheses with A being opening and B closing. And the language of a formula is, of course, a set of words that are satisfying that formula. Why am I mentioning that? Okay, well, okay. This is the well parenthesized if we combine these two things. As many A's as B's, and there's no prefix that has more closing B than opening F. Some more exercises there. The temporal logic that is so defined is called TL sharp. And what we could show, so temporal logic with counting in the past, and a little reminder of that logic over here. So it's a temporal logic, it's evaluated at the end, and we have a counting in the past. What is cool is that we already have lower bounds about this logic. We cannot express any prefix. There's two A's and any prefix. It's known. The technique is combinatorial. It's a bit graphical. It's actually very cool. And so we have that lower bound. We know that language is not expressible by TL sharp. So it is a bit surprising. Oh, yeah, as a bit of context, TL sharp is included in our threshold circuits. It's even included in our threshold circuits of linear size. They're very small. All right, and here's a kicker. Transformer languages are exactly those expressible in that temporal logic. From that, we have lower bounds against it. We know that transformers cannot do two A's in a row, which seems surprising a little bit. But all right, so the idea, it's pretty much the same proof. Gonna skip that quickly. And you may be like, oh, this is nonsense. I know that my ChatGPT, even without chain of thought, I guess, can do. There's two A's in my word, and yes, I've mentioned I lied a few times, and the fact is that with positional encoding, with more information about the position of stuff, I could do this. I could make, in my embedding of the input, information that says that this character is next to this character. And then I can check that this pattern doesn't appear. But this can be actually, we can trick the positional encoding by adding a letter that can appear anywhere. It's called a neutral letter. It can appear anywhere. So that means that these two A's can be separated by a letter E as much as I want. And then that language with that neutral letter is not doable by transformer. Which is, I mean, this is very weak. But that's why chain of thought is so crucial in modern AI. All right, so let me just wrap up with something slightly more precise. We have a depth hierarchy for TL sharp. And the depth hierarchy translates to a depth hierarchy for transformers. So a transformer of a specific depth can do something that a lower depth cannot do. And that language is the words over AB that alternates K times between A's and B's. So this alternates 3 times 1, 2, for example. Okay, and we can prove that using the same technique as the one with TL sharp, that this is doable with K layers, but not K minus 1 layers. And you may be thinking, wow, but that language seems very doable with my transformers. Sure, it's because you've never trying to train a transformer over 42 different alternations of A and B's. They're just not good at that. Or you would need 42 layers. In the paper, we, of course, because it's an AI paper, we have graphics. Okay, actually, they got better. They got better from that time here. But we were training transformers on these languages and showing that with a certain depth, you couldn't do too many alternations. All right, they're trained over inputs of size 0.50. And then we're testing them over inputs of bigger length. So this is called length generalization. And this logic here has been proved more recently in the last 3 months to be a, depending on your formalization, but exactly what transformers can length generalize for. So they can be learning on a smaller input size and generalize to longer input sizes. All right, let me wrap up here. So transformers are just a bunch of most linear operations. That's it. And there's a lot of parameters, and this is what it's trained. If they're allowed to think, they're Turing complete, but this is not a feature of transformers per se. Any stupid old model can actually have that trick embedded as long as they can count a little bit. As language acceptors, when I just put a threshold over the size, the output is positive, so I accept my word. They are expressible using threshold circuits, more specifically linear size threshold circuits. They're exactly equivalent, more or less. This is the input encoding to TL sharp. And we have extensions of that result with different positional encodings. And a depth hierarchy can be deduced from that characterization. So main question, learnability versus expressiveness. That's a very important question. There's some good answers that have been provided in the last 3 months. It's an 82-page paper, so you will excuse me, I've not read it yet. But Andy, the collaborator on the Andy Young, is on that paper. And they show that TL sharp corresponds to what is learnable. Fix the lies. We've fixed quite a few lies with positional encoding. We've extended these results to positional encodings, but not completely general. And there's been a question that was asked about that's smaller than I. Can transformers contribute to circuit complexity? Here we have circuit complexity contributing to transformer study. And there was this quote like a few years ago was saying, it was suggested that unconditional lower bounds against encoder-only transformer would imply breakthrough circuit lower bounds against linear threshold circuits. Our results avoids this barrier by exploiting the information bottleneck and autoregressive nature of decoder-only models. And our proof crucially depends on the fact that in decoder-only models, each token cannot attend to any token after it. And this is that J smaller than I. It shows up here. Everything is easier because of that J smaller than I. We get temporal logic. We got first order logic, but with only 2 variables for which we can deduce explicitness results. And if it weren't for that, we couldn't be saying much because there would be huge circuit lower bounds that would be required to prove any kind of results. And that's it. Thank you for your attention. So, yeah.
Where does it come up now? Is it just in the back arrow of the TL?
So that's, we could maybe have a precise characterization, but we cannot have a depth hierarchy because no depth hierarchy is known for threshold circuits. So, or for linear size threshold circuits. So if you could prove that without the J smaller than I, you would have a huge result in circuit complexity. While here we're using circuit complexity results that existed, we generalized them somehow, but that existed. And so there's no breakthrough coming back to 1960s problems.
But my question was, where is it necessary to have that? Because you mentioned the future.
It's in the chart. So we can only count to the left.
Yes.
Is it just there that it's needed?
It is just that. It is just that the logic for, if you had also the future, would be you have accounting in the past and accounting in the future. And then the lower bounds don't work, really, they don't work. Yep. Any other questions? I would encourage you to read, what do I have? This is our latest paper. It's submitted, but this, if you're interested in algebra, this is the algebraic version of what we did. And there's a exactarization of the regular languages that are implementable in transformers. And so like exact and decidable. So I can tell you exactly which are the regular languages that your transformers can do. All right.
Other question? Let's thank the speaker again.
Thank you. Vrai.